check this one out. We have a variable that is an exponent, which makes this one exponential. How fun that one's going to be. All right, let's pick a few values around the origin, and we will graph this thing. 2 to the x. It's not 2 times x, it's 2 to the x. We've graphed 2 to the x. That one's linear. Let's go -2, -1, 0, 1, 2, 3. We'll go a little bit further, and we'll start at the bottom. So this would be 2 to the third. 2 to the third is not 6, that is 8. 2 to the second is 4. 2 to the 1 is 2. 2 to the 0. Okay, you can see a pattern here, right? Okay, I think it's really worth saying there's a pattern going on here. That's why I started at the bottom. Okay, I started at the bottom kind of on accident, and the pattern just shows up. But notice the pattern here. If you don't know what 2 to the 0 is, it's okay. I'll go ahead and tell you it's 1. But you can see that from the fact that my exponents are decreasing by 1, and these numbers are half. So half of 8 is 4, half of 4 is 2, half of 2 is 1. So let's keep going. If you don't know what negative exponents do, you're about to find out. So if I continue this pattern, so half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is a half. Oh, so what was 2 to the -1? This 2 with a negative exponent, it moved down. The 2 became 2 to the first in the denominator. And now if we take half of a half, we get 1/4, because 2 squared is 4, but the exponent was negative, so it throws it in the opposite place of where it is, so it's now in the denominator. Let's graph these. Okay, there'll be more conversations about that later. Let's graph this. Let's start at the origin. Well, let's start on the y-axis, 0, 1. And if you're looking for a shortcut on how to graph them, well, good luck. But you can get a good starting point. In a sense, like slope-intercept, but it's not. You can at least get the intercept. And the intercept is this understood 1 right here. Okay, just saying. Like in this case, it's going to be a 4. Throwing that at you. Hope it sticks. Okay, 0, 1, 1, 2, 2, 4, 3, 8. There we go. We've graphed those. Now we're going to graph on the other side. -1, 1/2. Ooh, not landing on a grid mark. That makes me sad. -2, 1/4. Ooh, even harder to graph. If we kept going, it would be 1/8, 1/16, and it would get closer and closer to, but never touch, the x-axis. There are going to be some massive conversations about what that means, what it looks like, how we can represent that later. This lesson is one of these beautiful things that just introduces you to a lot of cool stuff. And one of those things is the fact that we will never actually touch the x-axis in this case. So let's graph forward first. If you ever hear someone saying, man, this thing grew exponentially, that means it grew really fast, like really big, really fast. Man, the national debt is increasing exponentially. Actually, it's not exponential. It's probably linear, but it seems that way because the number's so big. If you continue graphing this one, do not cross the x-axis. It should get closer to, but never touch, which I didn't do a very good job of by hand, but it's that. Okay, so that one's exponential. Let's graph the next one, which is the exact same thing. Let's put some parentheses up in here, though. Do you have to have them? No, but it does help me explain what's about to happen. Grouped with your x is a +1. So it's everything you just did, but now it's shifted. Now, we could do the table of values. We totally could, and I might. I'm still debating it. But it's the same idea that we've had a couple times before where grouped with your x, that's your horizontal shift, and you're going to change the sign of that. Like, ooh, I'm going to go -5. I'm going to go -1. So everything you just graphed here is going to be shifted left 1. So we're going to not be here, we're going to be here. We're not going to be here. This was at 1, 2. We're going to go left 1. All right, we were at 2, 4. Now we're going to back up 1. We were at 3, 8. We're going to go left 1. Now it's a 2, 8. We were at -1, 1/2. Now we're at -2, 1/2. We were at -2, 1/4. So now we're at -3, 1/4, which is even harder to do as we graph along the x-axis this time. Okay, let's connect them. So what do you think? Should I make a table of values? Let's not. Okay, don't cross that x-axis. Those are exponential. Let's do the next one, which is also exponential. But there is not a set parent function for exponential graphs. Okay, let's talk vocabulary for just a second. A parent function is like the function you start with. That's a parent function. And you can do all kinds of stuff to it. Flip it over and add 3. Put a negative and add 3, and flips it over. But this looks like its parent. So parent function, offspring function, I don't know. So in these specific families of functions, we would start with something really basic like 1x. And then we would say, okay, maybe it's 2x, or maybe it's negative 1/2 x minus 1. And we start moving all kinds of things around. But the most basic formula, basic form of a function is its parent function, which we have done at the beginning of each one. It's cubic, square root, cube root. But now that we get to exponential, there's not a set parent function. Because this could be a 2, it could be a 3, it could be a 1/2. This one's 1/2, but then there's a 4 in the front. So let's make a table of values on this one. We won't do a table of values on that one. Don't cry, don't cry. Y equals 4 times 1/2 to the x. There we go, there we go. All right, let's pick some numbers around the origin. So yeah, 0, 1, 2, 3. Let's go -1, -2. Yeah, as far as I'll be able to go. Let's start at the bottom, 3. So 4 times 1/2 to the 3rd power. If I cubed 1/2, I'd have 1/8. Cube the 1, it's 1. Cube the 2, it's 8. 1/8 of 4 is a half. That means that we are going to be at 3, 1/2. You can probably see where this one's going. Where this one hovered over the negative end of the x-axis, this one's going to hover over the positive end of the x-axis. Okay. Hover is not the mathematical term we're going for. 4 times 1/2 squared. If I squared a half, I'd get 1/4. So 4 times 1/4 is 1. So 2, 1. 4 times 1/2 to the 1, it's going to be, well, 4 times 1/2, which is 2. Okay, so 1, 2. All right, 4 times 1/2 to the 0. Well, anything to the 0 power is 1 except 0. 0 to the 0 power is indeterminate. Desmos doesn't think so, but we'll have those conversations later. Maybe. Okay. 4, now it's getting fun, times 1/2 to the -1. Okay, what's 1/2 to the -1? Well, it flips it over. So it's going to reciprocate this thing. So we're still going to have our 4, but we're going to have 2 over 1 instead. That's going to give me an 8. So there's that one. -1, 8. And then we're going to have this -2 that's just going to be way the snot up there. And I'll go ahead and tell you, this one's going to be a 16. I want to show the work because it's fun. But 4 times 1/2 to the -2. That's going to give me 4 times, okay, let's flip it over because it's negative, and that makes it 2. But now we'll square it, which makes it 4. And so there's where your 16 comes from. If you didn't catch that, it's okay. All right, if you were to proceed, this would be a half, this one would be 1/4, this one would be 1/8, 1/16. It's going to get closer and closer to the x-axis, but never actually touch it. So don't touch that x-axis. Don't you do it. Oops, shouldn't have that bump there, but it does. There it is. Okay, we have dealt with 3 exponential. I do want to point out the difference in these, and I think it's worth labeling in a different color. This one is going to be exponential growth, and this one is also exponential growth, and I would like to think it's obvious why, but it's because the graph is going up. Let's also talk about the fact that on each of these, as you move from one integer to the next, you're doubling, okay? This one, instead of growth, would be called exponential decay, and the reason why is because it's going down, but as you go from one integer to the next, you are halving.